Hello students, welcome back to SapphireBlueChemspark. Let us start our today's session, the chapter Coordination Compounds from Inorganic Chemistry. So the previous session we discussed about crystal field theory, in which we have explained about the octahedral complexes and tetrahedral complexes, where we studied about the splitting of d orbital in presence of the ligand. That means it may give rise to the two sets of d orbital, T2g orbital and Eg orbital. In octahedral complexes, we said the T2g orbital is lowered in energy and Eg orbital is raised in its energy. But in the case of tetrahedral complexes, we discussed the splitting of d orbital that makes into the two different states. One is T2g and other one is Eg. But T2g gets raised in energy and Eg gets lowered in its energy. And we know well the T2g orbital has 3 orientation and Eg orbital has 2 orientation. So both of them can accommodate. T2g orbital can have of 6 electron and Eg orbital can have 4 electron. So now we are going to discuss about what is crystal field stabilization energy. Because in those two type of complexes, we said the complexes becomes stable based on the splitting of d orbital. So how those complexes become stable, that is what explained in terms of crystal field stabilization energy. The crystal field stabilization energy is nothing but the amount of stabilization provided by the splitting of d orbital into two sets is called crystal field stabilization energy. So upon splitting of d orbital, the electrons they can go for either T2g orbital or even Eg orbital. So when electron enters into T2g orbital, where each electron acquires the energy of minus 0.4. And we know well during the splitting of d orbital, the T2g set they have the electrons in the case of 2 by 5 and Eg set we said 3 by 5. T2g set is lowered by minus, Eg set is raised by energy. So by solving 2 by 5 is equal to minus 0.4 plus 3 by 5 is equal to plus 0.6. So based on this, we may know each electron present in T2g orbital can have minus 0.4 and the electrons in Eg orbital can have plus 0.6. So based on that, we can calculate the CFSE, crystal field stabilization energy, is equal to the total number of electrons present in T2g orbital multiplied by minus 0.4 plus the total number of electrons present in Eg orbital is multiplied with 0.6. So this is nothing but an algebraic sum of the electrons in T2g orbital and Eg orbital gives rise to CFSE, that is crystal field stabilization energy. Let us discuss about the crystal field stabilization energy for the various d orbital system. We can have d1 system, d2 system, d3 system, d4, d5 like that. So because d orbital can have the electrons of 1 to 10. So let us find first of all d1 system. D1 system can be explained for titanium 3 plus ion. Titanium atomic number 22. Its electronic configuration 3d2 4s2. So by losing 3 electron it becomes 3d1. So where it has only 1 electron, that electron should always goes to T2g orbital because we are discussing about octahedral complexes. So the 1 electron when it goes to T2g orbital, then the crystal field stabilization energy of D1 system is minus 0.4 dq. For D2 system we can take vanadium 3 plus ion Vanadium 3 plus ion whose atomic number is 23. So its electronic configuration 3d3 4s2. By losing 3 electron, it becomes a d2 orbital. So as it has 2 electron, because of the lowering of T2g orbital, we know that 2 electrons should enter to T2g orbital. But how it will enter? Both orbital can have 1 electron. According to Hund's rule of multiplicity, all the available orbital until it contains 1 electron, no pairing will take place. That's why the 2 electron that occupy the T2g orbital, where we are getting the stabilization energy of minus 0.8 dq. For D3 system, we can take chromium 3 plus ion. Chromium atomic number 24. 24 that can be written as 3d4, 4s2. When we lose the 3 electron, it becomes D3 system. Here they have 3 electrons, so all the 3 electrons should enter to T2g orbital. So it becomes 3 into minus 0.4 equal to minus 1.2 dq. Let us find the D4 system. D4 system can be taken for Mn 3 plus ion. Manganese atomic number 25, so we can write D5 4s2. So by losing 3 electron, it becomes D4 system. When we have 4 electrons in d orbital, that can have the 2 possibilities of the electrons enter to T2g orbital and Eg orbital. One way, all the 4 electrons can accommodate in T2g orbital. So in this T2g orbital, one of it will have a pair electron, the other 2 will have single electron. So we may find like this. But in the case of, if all the 4 electron enters into T2g and Eg, the T2g will have 3 electrons in its singlet and Eg orbital also have 1 singlet electron. So how this is decided? The electron enters into either T2g orbital alone or T2g and Eg orbital. How it is decided? This is what decided by the strength of the ligand. Suppose if I have a strong field ligand, what happen? All the 4 electrons of d orbital can enter to T2g orbital itself, where the complex will be low spin because it has one of the paired electron and 2 unpaired electron is alone there. Suppose if I have weak field ligand, the complex will be high spin. This is why these T2g and Eg orbital, they have all the electrons are singlet electron and hence it becomes high spin. So while comparing, here one of the electron gets paired. How the pairing will take place? This pairing, that is because of pairing energy. What do you mean by pairing energy? Pairing energy is the amount of energy required to pair the electrons in the given orbital. That is called pairing energy. So, due to the pairing of electron in its T2g orbital, we have to compare crystal field stabilization energy with the pairing energy. When crystal field stabilization energy is greater than the pairing energy, what happens? The electrons will get paired up in its lower energy orbital itself. Or if the del dot value, that is the crystal field stabilization energy of octahedral complexes, is less than pairing energy, then none of the electrons will be paired. It has to enter into lower energy state as well as higher energy state of T2g and Eg. So we will get T2g3, Eg1. So when the d orbital have more than 3 electron, there we have to compare the strength of crystal field stabilization energy with pairing energy. Based on that only the electron can enter into their orbitals. Okay. Suppose if I have T2G4Eg, what happen? I should add the pairing energy along the crystal field stabilization energy, that makes the net crystal field stabilization energy of the complex. So CFSE is equal to what? The 4 electron present in T2G orbital. Each orbital electron can have minus 0.4 value. So 4 into 4, it becomes minus 1.6 dq. The net CFSE becomes the sum of minus 1.6 dq plus pairing energy. How many paired electron I have? Only one set of paired electron I have. So what I can do? This is 1 into pairing energy. I can multiply and should add with the minus 1.6 dq. Okay, suppose if I have T2G3Eg1 orbital, now what happened? The 3 electron in its lower energy state and 1 electron in its higher energy state. Lower energy state it becomes minus 1.2, higher energy state it becomes plus 0.6. Minus 1.2 plus 0.6, that makes minus 0.6 dq. So for this type of complexes, the net CFSE becomes equal to the sum of crystal field stabilization energy plus pairing energy. And you may find in this case none of the electron is paired up. So pairing energy becomes equal to 0. Correct? Okay. Let us find the calculation of CFSE for ion complexes, because we are going to have the d orbital having more than 3 electron. When it has more than 3 electron, that may find either pairing of electron in its lower energy state itself. So how pairing takes place in its lower energy? There it considers the pairing energy along with CFSE. CFSE is given by the product of number of electrons in T2G orbital minus 0.4 plus product of 0.6 into number of electrons in Eg orbital plus NP of P. What do you mean by NP of P? This is number of paired electrons in d orbital in presence of ligand field. And adding these all values from this, minus n dash of P is subtracted. So what do you mean by n dash of P? This is number of paired electron in d orbital in the absence of ligand field. So let us take an example of hexa-aqua iron 3 complex. In this I have the ligand water. So iron, its atomic number is 26, so its electronic configuration 3d6 4s2. Upon losing 3 electron, it becomes 3d5. So this d orbital can have 5 electron in its 5 orientation. If I consider this is as a high spin complex, the electronic configuration may go T2G3Eg2. Or if the complex is treated as a low spin complex, then it becomes T2G5Eg0. Let us find the net stabilization energy of this complex. So when I have 3 electron and 2 electron in T2G Eg, I may find minus 1.2 plus 1.2, so the net value becomes equal to 0. And it has no paired electron either in the absence of ligand field or even in presence of ligand field. So, and hence the NP of P minus N dash of P is also equal to 0. Let us take low spin complex. Low spin complex, the T2G orbital has 5 electron. So out of 5 electron, 2 of them gets paired. The third electron is the singlet one. The third orientation has singlet electron. So now you can find all the 5 electron as it is in T2G orbital. This becomes equal to minus 2 of del naught plus 2p. Why 2p? Because of the presence of 2 paired electron in T2G orbital. Let us consider the water that absorbs the frequency of light about 14,000, or I can say the wave number of water is 14,000, and the pairing energy of this one becomes 30,000 centimeter power minus 1. I can substitute P equal to 30,000 and what is that? Del naught equal to 14,000. By the difference, I will get 32,000 per centimeter. Comparing the values of 32,000 with the 0, I may find the high spin complex of this one is more favorable than low spin. This is why, because the energy difference is highly positive compared to 0. So, we can conclude that the hydrate complex of iron is a high spin complex and it never be a low spin. So, because of that calculation CFSE that determines it is more favorable for high spin complex, not for low spin complex. We can have another example. In the place of water, we can take cyanide ligand. In this case, cyanide, it has the wave number of 35,000 and pairing energy as such. For iron complexes, the pairing energy is 30,000. So, 2 into 30,000. You may find the difference of energy is 10,000 minus 10,000. Compare. For high spin complex equal to 0, low spin complex equal to minus 10,000. CFSE, as far as it is lowered, the formation of complexes will be more favorable. Therefore, this complex is able to low spin complexes. It cannot be a high spin complexes. So, such a way only we can able to discuss about the stability of the complexes in terms of crystal field stabilization energy. So, crystal field stabilization energy is helpful in determining whether the complex is a high spin complex or low spin complex in terms of pairing energy and crystal field splitting energy. Followed by crystal field stabilization energy, let us find what are the important factors that may govern the magnitude of crystal field splitting energy, that is del. So, the magnitude of CFSE actually depends on the central metal atom or the ion to which subgroup it belongs, because all the transition elements, they belong to the group of 3 to 12. So, we have 10 groups under the D block elements and they may have the different series, 3D series, 4D series, 5D series, 6D series, depends on in which period it is accommodating. So, when period number increases, what happens? The tendency of the splitting of d orbital also increases and it is found to be about 30% to 50% increases for the elements of same subgroup on going down the group. You may find the elements of same subgroup can have the increasing del since the n value increases. N value is nothing but the period number or the principal quantum number. So, when the number of period increases, the elements belong to the same group. The splitting of del value, the crystal field stabilization energy also increases. The next one, oxidation state of metal ion. The transition metal, they can have variable oxidation state from lower to the highest +8 we can say. So, when oxidation state increases, the size of the metal ion decreases. So, greater the charge, smaller the size will have more polarizing power. So, because of its more polarizing power, the ligand's orbital that can approach the central metal ion more effectively and hence a large splitting of d orbital can take place. So, when oxidation state of metal ion increases, the magnitude of crystal field stabilization energy also increases. The next one, nature of ligands. Ligands we said actually low weak field ligands and strong field ligands. How the strength of ligands is being determined, that can be determined based on their energy concerning. For example, energy is given by H nu. Here we are considering the energy of crystal field splitting we are taking. That's why E is replaced by del. So delta equal to H nu. Delta is nothing but crystal field stabilization energy equal to H nu. Nu equal to C by lambda or 1 by lambda equal to nu bar. That is nothing but wave number. So a particular ligand that can absorb a suitable wave number of light in a given frequency where they may find different amount of energy when it is calculated for 1 mole of the complex. So Hc nu bar we have, H is the Planck's constant, C is the speed of light and nu bar is wave number of the ligand. So let us find the 3 different complexes, hexabromido titanate 3 minus and hexafluorido titanate 3 minus and hexa aqua titanium 3 plus. In these cases we may find 3 different ligands. These 3 different ligands, they have their wave number of 12,500, 19,000 and 20,000. So when this wave number differs, the magnitude of del also changes. And this is calculated as the energy, but actually we have to determine energy of the complexes for 1 mole. 1 mole is nothing but its molar mass, and 1 mole that may contain only Avogadro number of particles, and hence the product is multiplied with the Avogadro number. We are getting 149.4 kilojoule for bromide complex, 227.7 for fluoride complex and 239.7 for aqua complex. So you can arrange these ligands based on their energy. You may find fluoride, bromide is less than fluoride less than water. The same order we can find over here. Iodide less than bromide, less than fluoride, less than water. So this spectrochemical series is arrived by the different absorption of suitable wave number of light by the different kinds of ligands. So the arrangement of these ligands in their increasing order of splitting of d orbital is given as a spectrochemical series. So the splitting of CFSE also depending upon nature of ligand, and we may find the lower extreme left end of the series are weak field ligand and the higher, the extreme right end of the ligands are strong field ligands. The next one, the geometry of complex. We have 2 types of splitting only we discussed for crystal field theory. One is tetrahedral splitting and octahedral splitting. The tetrahedral splitting is observed about 50% as large as that in octahedral complexes, because in tetrahedral complexes the direction of orientation of d orbital with the ligand orbital never same. These are the important factors that governs the magnitude of splitting of crystal field stabilization energy. The next one, color of the complexes. The most distinctive property of coordination compounds is the formation of wide range of colors, which will vary depends on the nature of the ligand also. And we already studied about the color of transition metal ion, that is due to the dd transition of electron. That means the electron within the d orbital, it may go the transition from lower energy to higher energy. The same principle is applied even in the complexes. But how the complex that may exhibit the different color for the different types of ligand. This is because we have the different types of ligands, weak field as well as strong field ligand. So based on the nature of the ligand, when we pass a white light through the sample of the complex, let us remove a small amount of visible spectrum from the white light. After passing through the complex, the emerged light, when we analyze, the complex would not possess the white, that means the colorless. Actually, it becomes a colored one. Even after the removal of visible spectrum from the white light, the emerged light that provides color to the complex. That is what said to be complementary color of the complexes. Complementary is means when the white light passes through the sample, some of the light is being absorbed by the complex, and when it is coming out of the complex, the emerged light, the wavelength which is left over in the complex, that provides complementary color to the complex. Let us take an example of hexa-aqua titanium 3+ ion. In titanium, the electron which is present in 3d orbital and it has only one electron. So, in its ground state, actually the electron is present in T2g orbital and Eg orbital is empty. When a white light passes through the complex it absorbs some amount of frequency of light in the region of yellow-green. Based on that, as the energy is absorbed by the electron, it gets excited to higher energy state of Eg. So, where the electronic configuration becomes T2G0 to Eg1 in its excited state, where the color of the complex it becomes the violet color. That is what said to be complementary color. So, the excited electron it never be over there, it has to come back to its original energy state. So, by that time the amount of energy absorbed by the complex will be emerged out. So, it takes the complementary color of yellow-green is violet color and hence the complex it possesses violet color. Then the color of the complex actually depends upon the magnitude of crystal field splitting energy as well as the ligand field, whether it is a strong field ligand or a weak field ligand. Based on that, the complexes that can have its color. At the same time, the complexes in the absence of ligands, they do not exhibit color. We can have the same type of the complex. Let us take titanium hexa-aqua 3-chloride. So, TiH2O 6 times Cl3. When it is heated, what happen? All the 6 water molecule is lost by the complex. So, the salt it becomes colorless. So, a violet colored salt it becomes colorless in the absence of ligand. So, the complexes are actually in colored state due to the presence of ligands only. Then we said when the nature of ligand changes, color of the complexes also changes. That can also be explained by taking an example of hexa-aqua nickel 2+ ion. When all the 6 ligands are water, the color of the complex is green. When this aqueous solution is treated with 1 mole of ethane 1,2 diamine and it is a didendate ligand. So, it can replace 2 molecules of water from the 6 water molecule and hence it becomes the ethane 1,2 diamine 1 time present and water present 4 times. So, when 2 of the water molecule replaced by En, that is ethane 1,2 diamine, color changes from green to pale blue. And in another case, when another 2 molecules of water is replaced by 1 mole of ethane 1,2 diamine, it becomes En twice, H2O twice. The color changes from pale blue to purple. When all the water molecule is replaced by ethane 1,2 diamine, the color of the complex it becomes violet. So, the complexes having the color also depending upon the nature of the ligand present in it. Okay, let us find what are the limitations of crystal field theory. This crystal field theory, it does not account for the presence of covalent character in the complexes. We know the metal in its higher oxidation state gets smaller size and it has more polarizing power. So, the ligands can approach the metal ion more effectively and it can bring out a DD splitting, the d orbital splitting to greater extent. So, this is according to Fajan's rule, smaller the size of cation and greater the charge of cation getting more polarizing. So, the compound will have a covalent nature, but in CFT theory that does not account for the presence of covalent bond in complex compound. And one more, it also discuss about the ligands, the crystal field theory that assumes that all the ligands are as point charges. Those point charges are metal ion as well as the ligand. When it considers the point charges, we can have the anion as well as the neutral ligand. So when we have anionic ligand, that must have the greater splitting effect of d orbital, and it must be the strong field ligand. But in the spectrochemical series, all these anionic ligands that lie to the low end of the spectrochemical series, that means those are in the case of weak field ligand, and most of the neutral ligands are found to be in strong field ligand. This is what it is unable to explain about that. These are the limitations of crystal field theory. Okay students, let us close our today's session, and we will continue the same chapter in our following sessions also. Until then, bye bye.